Okay, today we're going to learn about the ratio test. Okay, the ratio test is we're going to let the summation of a to the n be a series with non-zero terms. If the series, the summation of a sub n, converges absolutely, then the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. The series summation of a sub n diverges when the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is greater than 1, or the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n equals infinity. Then we have a divergent series. The ratio test is inconclusive or fails when the limit as n goes to infinity of the absolute value of a sub n plus 1 term divided by the a sub n term equals 1. So converges if our ratio of our a sub n plus 1 term over a sub n is less than 1. Diverges if that ratio is greater than 1 or equal to infinity. And it is inconclusive if that ratio equals 1. That's the ratio test. Now, this is very useful with any series that has factorials or exponentials, is where this test comes in very handy. Okay, let's try an example. Test the series, the summation of n equals 1 to infinity of negative 1 to the n of n cubed over 3 to the n for absolute convergence. Now, I'm going to do my a sub n plus 1, so I'm going to add 1 to each of my n terms. And I'm going to divide by the given series, where it is n is n. Now, first thing you notice, because of the absolute value sign, that negative 1 to the n plus 1 and the negative 1 to the n term, that's just 1. So that's 1 over 1. So that just cancels out. So all we're really dealing with is the other part of the series, this alternating series here. And again, when we divide by a fraction, we're going to flip and multiply. All right, so now we're going to do a little algebra so that we can simplify this down. Well, I know 3 to the n plus 1 is the same as 3 to the n times 3. So I can rewrite the first fraction as the quantity n plus 1 cubed over n to the 3 to the n times 3. And then the second fraction, keep it the same, 3 to the n over n cubed. So the 3 to the n's cancel out. And so that leaves us in our coefficient 1/3, we can factor that out. So the limit as n goes to infinity of 1/3 of the absolute value of n plus 3 cubed over n cubed. And then we can factor that cubed out. And so factoring out that 1/3, we have the limit as n goes to infinity of, and then n plus 1 over n is the same as 1 plus 1 over n. And then remember our powers with limits, we could bring that limit into it and say the limit as n goes to infinity of 1 plus 1 over n quantity cubed times the 1/3. And then we know the limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 1 plus 0 is 0. So that leaves us with 1. So I have 1/3 times 1 cubed, which is just 1/3. 1/3 is less than 1. And by our ratio test, we can conclude that this converges absolutely. So converges absolutely by the ratio test because we had a limit value less than 1 for that ratio. Okay, for our second one here, we're going to do the limit as n goes to infinity of n to the n over n factorial. So that's going to be, we do our a sub n plus 1 term, so we replace every n with n plus 1. And we're going to divide by the a sub term, which is the same as flipping and multiplying by our flip over our a sub n term. And then we need to do a little rewriting. I know that n plus 1 factorial is, n plus 1 to the n plus 1 power is the same as n plus 1 times n plus 1 to the n power. And I know n plus 1 factorial is the same as n plus 1 times n factorial. And so the n plus 1 on the numerator and denominator cancel out. Our n factorials cancel out. And we're left with limit as n goes to infinity of the absolute value of n plus 1 over n quantity to the nth power. Which, oh, that's familiar. That's the limit as n goes to infinity of the absolute value of 1 plus 1 over n to the nth power. And 1 plus 1 over n to the nth, that's the definition of E, if you remember from Cal 1. And so we can replace that and we can say that's the definition of E. So this is equal to E, which is greater than 1. E is greater than 1. So our conclusion by the ratio test is that this series diverges. Okay, let's look at this third one. We're going to determine whether this given series, the summation of n equals 1 to infinity of negative 1 to the n over n, the square root of n divided by n plus 1 converges or diverges. So we have the limit as the absolute value of the square root of n plus 1 over n plus 2 times n plus 1 over the square root of n, because we have our n plus 1 term divided by our a sub n term. And remember the negative ones, because the absolute value, we can just cancel those out and we don't have to worry about writing them. We can simplify this down, combining our square root terms together and grouping our non-square root terms together. Distributing our limit to each of our products, each of our terms here. And then now we're going to do the limit as n goes to infinity of the square root of n plus 1 over n. Well, that's the square root of the limit as n goes to infinity of 1 plus 1 over n, which we already figured out to be 1, times the limit as n goes to infinity of n plus 1 over n plus 2. And then for this second one, we'll use our end behavior model, and we can use our coefficient method here. So that limit is going to be equal to simply 1. And so I have 1 times 1, which is 1. My limit of the ratio, the absolute value of a sub n plus 1 over a sub n is equal to 1. Remember, if we get a limit that is equal to 1, our ratio test is inconclusive. And we have to throw it out. We can't test this using the ratio test. We got to try another technique. So I look at here and it looks like an alternating series. So let's apply the alternating series test and see if that could work. Sometimes it's trial and error. So that means our function f of x is going to be equal to our square root of x over x plus 1, or that's our a sub n term. And so remember, for alternating series, we need a positive function, a positive term. So that is positive. We need our derivative we need it to be a decreasing function. So we take the derivative of this function, and we get negative over a positive, which is negative. So it is less than 0. So that tells us for any x greater than 1 that this is a decreasing function. So we have positive, decreasing, and it's continuous everywhere except negative 1, but that's not in our domain, so it is continuous as well. So now we can do the limit as n goes to infinity of the square root of n divided by n plus 1. And so let's do L'Hopital's rule to evaluate this infinite limit. And we get the limit as n goes to infinity of 1 half x to the negative 1 half over 1. Getting rid of our negative exponent, that is equal to the limit as x goes to infinity of 1 over 2 to the square root of x. And that's a fraction, so that's equal to 0. And remember, we needed the limit to equal 0, so yes. And our conclusion is that this series converges by the alternating series test. But we are not done. Now that we know it converges by the alternating series test, we have to now check, is it conditionally convergent or absolutely convergent? To test and see if this is a conditional or absolute convergent, I'm going to use the limit comparison test. So if we're using the limit comparison test, let's compare our function to 1 over the square root of n, which is 1 over n to the 1 half. This is a p series. P is less than 1, so this is a divergent p series. And remember, the limit comparison is we take the limit as n goes to infinity of the absolute value of the square root of n over n plus 1 divided by our b sub n, 1 over the square root of n. And then when we divide it by a fraction, we flip and multiply the bottom fraction. And square root of n times square root of n is just n. And so that gives us 1 for the limit, which is greater than 0. And so the summation of the absolute value of a sub n diverges by the limit comparison test. So the original series converged, but the absolute value of the series diverged. So our conclusion is the original series converges conditionally. So this series is conditionally convergent.